to my left and to my right, and then the bathrooms are down the hall. Just for a brief second, I want to introduce our host, Rod Wetterskog. If you could give a brief round of applause for him.
Thanks, Justin. And well, good evening, everyone, and welcome to UT Dallas. For those of you who aren't familiar with our campus, we are about 31,000 students strong. We are a nerdy university. Even our School of Management are nerds. So we're really excited to welcome the SFPE to be here today. And Dr. Hezekiah, we're really excited to hear how we can keep our battle bots safe with our lithium-ion batteries. So we're excited to have all of you here. Our engineering program is comprised of electrical and computer engineering, biomedical engineering, materials science, systems engineering, computer science, and I believe I've missed one. That's six programs strong. And so we're really thrilled to have you. We're really excited to hear from our own UT Dallas students that have been working with Justin on some research projects as well. So if you've got any questions, a colleague of mine, Don, is back there. Don, if you raise his hand. If you've got any questions, especially if you're companies and you're interested in learning a little bit more how to engage with our brilliant students, just let us know. Once again, welcome, and we're thrilled to host you. Thanks.
Really quick, and we've got Dylan. There are committee chairs for our mentorship committee and our scholarship committee, so they both have a brief announcement to make.
Thank you, sir. So yes, everybody, I'm Greg Willis. I'm the chairman of the scholarship committee for the Dallas-Fort Worth SFPE. We've been doing $1,500 scholarships for about 20 years now, and this year we're happy to announce we have two $1,500 scholarships. For all you students out there, you can go to our website. We put all the applications online. We streamlined it. Not too hard to do, just some short, little bit of work to fill it out. We know you guys are all busy, but would love to see a good, rich class of applicants out there. Appreciate it. Hey, we got two of them.
Hi, my name is Dylan Gruing. For those of you that don't know me, I'm your Vice President of the Society of Fire Protection Engineers here in Dallas-Fort Worth area. I wanted to take this moment to introduce you to a program that we offer to students that are interested in the field of fire protection engineering. So it's called our Mentor Program, and what we do is we pair students with mentors, and the mentors meet with the students 3 times a semester, 1 hour a month. Basically, they can meet in person if you're here local, over dinner, lunch, coffee, or virtually or over the phone. And for the students that are interested in doing it, we let you select different fields that you're interested in within our fire protection and safety engineering realm, whether it be forensics, whether it be government official, or fire sprinkler design, fire alarm, traditional engineering, things of that nature. So if you're interested in doing that, we'll have flyers at the end, and you can come talk with me. It's free to apply, free to partake in it. It's a great opportunity to get to know folks in the industry. It's also a very good opportunity for you to get to network with people. We had 2 students receive internship offers last fall and 1 receive a full-time job offer. So it's a great opportunity to get yourself out there and meet with these companies. And for those of you that are involved in the companies, if you're interested in being a mentor, come speak with me after as well. It's just a quick form. We'll get your name, phone number, email, the industry sectors you've worked in. Students will put the same thing with the industries that they're interested in, and we'll connect you all next fall to start meeting and kind of reassign with different folks so you can get to grow your network before you graduate and hopefully join us in the field of fire protection engineering. So just come find us after. And then also, we'd like to take a quick moment. For those of you that don't know Justin Milne, Justin has been an integral part of the Society of Fire Protection Engineers in Dallas-Fort Worth since we came back after the pandemic. We kind of fell off our rocker there, and he's been especially helpful in helping us come back. And he's been with us for 2 years now, and as a thank you for all of his time and energy and efforts, we're presenting to him a plaque from the National Society of Fire Protection Engineers as a token of gratitude, as well as a past president pin. As this is going to be his last month or 2 with us as president, we've been very grateful for all he's done for us. So thanks, Justin.
Thanks, Dylan.
Thanks, everybody.
The camera guy.
All right, thank you all.
Yeah, I'm off to French Polynesia, so I get married next week too. So I'm very excited. Thanks to my lovely fiance for supporting me in doing this. Okay, so the next thing we have on the agenda, yes, we have a leadership transition. So these fine people are also stepping up. We have a very special presenter, one of our very own here at UTD. So I want to introduce Mrs. Lonnie Wolf. She's going to present on some research she's doing. Yeah, come on.
Hey, so my name is Lonnie.
Lonnie, one sec.
That will make it better. So my name is Lonnie Wolf, and right now I am conducting research on fire pump sizing. The current approach to fire pump sizing for fire safety systems is using an algebraic approach using the Hayes-Williams equation. With the properties of the system that you're intending to design, you can use this to calculate the approximate frictional pressure loss due to your piping. However, you can also calculate this pressure loss with a CFD approach using software like ANSYS or StarCCM. This may yield you some more accurate results because you can simulate the system more similarly to how it would behave in real life. Here are the governing principles of both of these approaches. You can see the Hayes-Williams equation here and all the variables involved, all the properties of your system. The Navier-Stokes equation is not something that we will be solving by hand. This is something that the CFD software will be using. Here's a picture of the test meshes the test geometry that we'll be using before we move on to a more advanced geometry. The cross-sectional area here that you'll see to the right is what this will be the cross-section of the fluid that we're simulating. If you notice, the mesh gets more fine towards the boundary layer, which is where the fluid, in this case water, would meet the pipe. It's more fine around this area because it'll yield us more accurate results. This is the area that we'll be most worried about, so it's very important that we have these accurate results. Here's a picture of what that mesh looks like fully fleshed out. It's got about 200,000 volume elements in it. The more elements should yield even more accurate results. This is just an example picture of one of the simulations that we've run using this test piece of piping. The residuals will converge to a value, as you can see, as you go to the right. It'll turn into a straight line, and that's how you know that the solution to your simulation has converged. It's not going to change anymore. On the next slide, you can see one of the monitors that I used for these test simulations for our grid convergence study. If you'll go to, would you mind going to the slide after that? Here's what that grid convergence mini-study looks like. We tested this test piece of pipe at different grid resolutions, which is using a different number of elements. We used 5 different numbers of volume elements, and as you can see, the chart, the trend line starts to converge. The values between the tests get lower and lower. This is how you know that your results are pretty accurate. You don't need to worry about there being a large source of error here. If you'll see, you can see here, on the left is a cutaway cross-section of the middle of this pipe. This is velocity contour. You can see how fast the fluid's moving at any point in this piping system. On the right, you can see the pressure contours of the wall. Here is the model of the building that we're going to be using for the final stage of our study, provided by yours truly, Justin. And on the lower left of this, you can see the inlet pipe to the whole sprinkler system on the inside. On the next slide, you can see a close-up of some of that piping and also a sprinkler. For the future of this study, we will be applying the principles that we agreed upon in our test studies, like the geometry, the resolution of the mesh, to this more complicated real-life case, because it's more applicable to in real life. We will be comparing the results of that to our algebraically hand-solved pressure loss to the simulation. And we'll be reporting all of these results at the National Fire Protection Association Conference and Expo in Orlando this summer. Thank you for listening.
Thanks, Lonnie. So now we have a guest with us from University of Texas at Austin. So it's my pleasure to introduce to you Dr. Ezikoye, aka DK. So give it up for Professor DK. Dr. DK.
Is that acceptable? Yeah. Ooh, it's on my laptop. Yeah, is it HDMI?
Rod, do you know if you can log in with his laptop? Or Lonnie?
I would imagine this would work. It's showing right now. Done this once or twice. So actually, while we're setting up and everything else, I wanted to thank, obviously, the DFW SFPE chapter, the award-winning, I should say, DFW SFPE chapter for having me here, Rod Wetterskog, Justin Mill, and Robert Hart. So thank you all for an incredible day. I really appreciate it. So I'm going to also mention, I'm also going to mention that I'm notoriously bad at determining how many slides to present, and I talk fast, so I apologize in advance, but you've been warned. And I think that part of it for me is that I really love this stuff, so it's getting there. So I really want to share sort of the things that we've been doing, the things that I've been learning with you all. So this is easy. This is the same system we use, I think. Oh, did they? I would imagine. I'm sorry, you just close this. Yeah. Well, if this is like UT Austin, then I should be able to put laptop HDMI, and that should work. So if this is like my classroom, that should work. Okay. So. I'm going to talk about lithium-ion systems, fire, and explosion engineering protection. So I guess just to start, I understand that there are a range of sort of levels of experience and expertise, so hopefully I'll touch on a bunch of things that are relevant to the different groups in here. So I run what we call the UT Fire Research Group, and we brand ourselves as working on emerging issues in fire science and fire safety. So right now, one of the most important issues, of course, is related to batteries and battery fires. But having said that, you know, we've worked on wildland fire issues before. Let's make sure this is working. Let's go back. I'm going to break my laser pointer here, trying to figure out how to get it to work. And as a safety person, I promise not to point this towards the crowd. That is, there it is. Oh, yeah, exactly. Yeah. So there are ties, obviously, to fire forensics. So we've worked on sort of, you know, it's sort of a little mathy, but sort of Bayesian methods to try to figure out hypothesis testing. Done a bunch on community scale fire risk and trying to understand, for example, the dependence on fire losses associated with fire department response time, and published extensively on that, on NFIRS issues. I think that one of the most important stakeholders in all of our work are the fire service, and so we work on firefighter safety. And as obviously it connects across all these, and sort of like at the sciencey level, and I'm not a scientist, I'm an engineer, we've worked on material flammability issues. So I think we're all going to be sort of aware of some of the issues in terms of the battery landscape, so I'm not going to spend too much time on that. Again, different levels of experience and expertise as far as the battery fundamentals, so we'll talk about that. And then we'll talk about research findings and applications. So, you know, there is an energy transition going. You could argue that this is a safety issue. You could say it's insurance. You know, there are a lot of things that people a lot smarter than I am have thought about as the reason why we have to have this energy transition. If it's going to happen, we're going to need ways of storing energy, and there are lots of different ways of storing energy. So electrochemical cells are not the only one. Having said that, anytime you store energy, there's the chance for some sort of hazard, right? It could be the Grand Teton dams. At the turn of the last century, there were issues in terms of boiler safety and boiler explosions. Hydrogen is great, but sometimes it fails also. LNG is a wonderful way of storing energy and transporting energy. It fails. And even a flywheel can fail. So all these are different ways of storing a lot of energy. If it's abruptly changed or changed in a negative way, an unexpected way, then there's a possibility for damage. So in general, batteries are safe, but there are conditions in which they fail catastrophically. And so you could argue that this is just an issue of immature technologies, that anytime you start with a new technology, there's a whole lot we don't know about how those systems fail. But, and it was interesting because I think Justin actually over lunch was talking about this, is that it's experience in failures that sort of gives this codes and standards process an opportunity to try to catch up in terms of providing new ways of designing so that, you know, accidents are no longer unknown, they become known, and we design hopefully against them. But then there still could be design code inadequacies, there's people make mistakes, which I know is probably a shocker in terms of this crowd, right? So people make mistakes and misuse, so that happens. But there could be defective designs, and so over time, presumably, known versus unknown changes, and this gap between why systems fail and not why they don't fail is different. So we're probably in the early stages for lithium-ion battery systems. And so you sort of have to forgive the process and try to, again, we'll do everything we can in terms of the, you know, design standards and codes issues to sort of ramp up, but that's one of the explanations. And fortunately, again, this crowd understands that there are a lot of different ways in which society changes technologies or adapts technologies. I'm not a huge fan of litigation, but litigation is one of those methods. In insurance, litigation, subrogation, there's a lot in the way that when things fail and there are warranties, whether it's a vehicle or otherwise, it's catching on fire, there's a lot that goes on in terms of loss of money that makes people change the way that they do things. And of course, there's just sort of a societal awareness that this isn't right. We shouldn't be having these types of losses based upon, again, things that we didn't know. Okay, so having said that, batteries have become part of everything that we do. And it goes from R&D testing, whether it's in the materials lab at UT Dallas or UT Austin or any other major university or company, to manufacturing. So this is an eVTOL company, so they're making electric vertical takeoff landing vehicles, and it's lithium-ion powered, or in the transports of batteries and assemblies of batteries, or in warehousing, this is Morris, Illinois, or in utility scale, this is the McMicken facility, Surprise, Arizona, or residential, so a customer, Hyundai Kona failed in a garage. We've seen, this is one of the early failures that we sort of like noted in 2019. Recently, there was one in Colorado with a Jeep, hybrid Jeep, that the garage door blew off because of a thermal runaway incident involving the battery. And then you say, well, geez, how about recycling? Well, in 2017, right outside of Houston, this train car was carrying spent lithium-ion batteries and the rail car. Can we turn on these lights at all? Or maybe I have that control. Yeah. Yeah, and the rail car exploded and shattered windows like a quarter mile, half a mile away. Fortunately, it wasn't in a densely populated area. So the point is that throughout the whole life cycle of these systems, there are going to be issues. And so how do we think about the failures and engineer against them? So, I think all engineers are designers. I mean, humans are designers. We design. And so I think oftentimes, though, we don't design for safety and liability. We may design for performance, we may design for cost, marketability, all sorts of reasons to design things, but oftentimes it's not for safety and liability associated with failure. Maybe we should, and I think that's what fire protection engineers do. We understand. I want to be a fire protection engineer, so I'm going to lump myself as we choose to understand consequences so that those can be put into sort of that design cycle. And so it could be a use issue in a building, it could be any other it could be an industrial facility, et cetera. And so that's an important aspect of how we do it. So now transitioning to sort of battery cells, et cetera, again, different sort of understandings of this. So you think conventionally or commonly, these are the components of a battery system, and it could be something as small as this little cylindrical cell. There are different formats of these types of cylindrical cells. It could be in pouch format, so these are soft, pliable pouches that contain the active battery materials, or it could be in a hard casing, but is not in a cylindrical format. And it's somewhat different in terms of its winding properties compared to these pouches, and sometimes different from the cylindrical cells. Now, obviously, all these different cells can be packaged in a different way. So they can be packaged into modules and then battery packs, and it doesn't matter what the original cell format is in terms of how they're packaged. And different companies feel that there are different competitive advantages in terms of what types of cells they choose, the size of the cells. So there's not one sort of size of cylindrical cells. There are ranges of them, and there's almost a trade-off between the capacity of the cell and the safety of the cell. So larger cells fail more catastrophically. It's harder to control them. So if you sort of dissect these cells, you find out that these are layered systems. And so the layered system consists of sort of these so-called active materials. And so most of the research right now is on the cathode material, the positive side of this system. This is on an aluminum current collector. It sort of repeats itself. So there's cathode on this side, there's cathode on that side, there's anode, which is usually graphite on this side, graphite on that side, and there's a separator, usually a plastic like polypropylene in between. And so this is a very thin segment. And funny enough, a lot of the modeling, like the detailed modeling, is just for this layer, but there could be tens or hundreds of layers within any given cell or more. So it's a question of how large the capacity is and what the issues are. And so it's a chemistry problem. So they call it redox chemistry, that you have to shuttle electrons through the circuit to complete the circuit. And so you can't have, in the absence of the electrons shuttling through the circuit, you don't have reactions. Well, why is that important? It's important because it gives us a sense of how long-lived that cell can be without self-discharging. So if I can't get chemistry to occur on either side of this system, then I can hold on to that cell for a long time until I connect it through an electrical circuit to have that occur. Okay, because they're chemical reactions, that's part of the problem and the challenge, right? Because of the safety issues. Now, as we think about lithium-ion batteries, and so, there's no test on this, but it's sort of interesting to note that there are a lot of different even lithium-ion chemistries that are sort of available right now. It's important to note that they all have different voltages, actually. So you could have, for example, 3-volt cases or 4-volt nominal cases. What that means is if I want to get a 12-volt system, I can either use 4 3-volt or 3 4-volt, but there's a difference in that. And there's also a difference in sort of like how many coulombs, how much charge each of them can hold on to per gram. And so there's a capacity issue. And of course, battery materials people want to go to higher and higher capacity. Why? Because if I charge it up, then I can drive across the country, in theory, right? But that's not going to happen anytime soon. But but the issue, of course, is that the higher the energy density, the more catastrophic the failure could be also, because when it releases, it's going to release a lot more energetically. And so some of the common materials that you hear are like lithium iron phosphate, lithium cobalt oxide, et cetera. And then, for all sorts of reasons, there's a push to get rid of cobalt as one of the materials. So these are metal oxide, lithium metal oxide cathode materials. And now there's a sort of a push towards sodium ion. I'm sort of pushing it back there in terms of where it is. And so, safe, certainly, in terms of the types of materials it uses, it's more abundant materials. Safety is to be shown and to be found in terms of measurements and analysis. So we'll just go on to the next. So the battery manufacturing process. So we just put together a battery fabrication facility where some of the folks from Jensen Hughes were helpful in terms of us commissioning it from the fire safety side. But it's a coating system, right? So there's slurries that mix together particles, and then you stick them on foil sheets, you squeeze them down, you cut them into sort of the right-sized elements, you assemble the cells, you cycle them to get them sort of ready, you degas them, and then you repackage them. So, the scales are huge. So everything from, human scale or vehicle scale to sort of like the material scale of these particle systems. So again, there's a lot of room in battery systems for understanding. Now, these are cathode particles, and why am I showing that? I'm showing it because for first responders and anybody who might be responding to a failure, we don't know how many of these potentially nanometer and sub-micrometer particles you're getting out. So when the cell fails, there's a jet of gas that's coming out, and it is scraping off this material and pushing it out. So these are important sort of measurements and considerations as we think about the safety of these systems. So on the anode side, those are cathode. On the anode side, the graphite is a flaky material, so we see sort of flakes, and in some sense we're less concerned about carbon. And you heard about, or you hear all the time about lithium metal batteries. And lithium metal batteries and solid state electrolytes sort of go together. And so the solid state electrolyte is that the shuttle for the lithium ions in conventional lithium ion batteries is through a liquid material, carbonate material that is flammable. So the idea in principle is that if all of a sudden we go to these solid state, these solid electrolytes, that we won't have that fire concern. Now, there are a lot of different issues, and this is an active area of study, is that, well, everybody seems to be finding that you still have to put a liquid electrolyte into it, so that's a concern. We don't know what the firefighting issues and suppression issues will be when we have lithium metal batteries, as an example. We just saw water is a great suppression agent, and so all of a sudden now what happens when we start having these types of systems? We don't know. A lot of these electrolytes have sulfur in them, so there's a potential for H2S, SO2. There's all sorts of toxicity issues. Some of them create cyanide when they burn. So there's a lot of stuff there, okay? But now, as we step away from sort of like the cell material level, sort of practically, let's talk about battery packs and battery management systems. So any of these cells by themselves is pretty useless unless it's in like a vape pen or something like that. And so anything more practical, you're gonna have to put together a bunch of cells. And you can put together these cells in either series or parallel. And if these are all operating on 3 to 4 volts, then I need to have a certain amount in series and a certain number in parallel to get a high enough voltage or to have enough capacity to do anything interesting or important. And so we'll talk about how that works. So in this case, we have 2 in series, 3 in parallel. So to get this 2S3P, 3 series, 2 parallel to get this 3S2P. And again, depending on the voltage, this is how we're going to stack it up. Sometimes you hear about a battery management system. And so the battery management system really is trying to deal with the complexity of these individual cells that are put together. One of the issues is that, and you think about an EV, which might have thousands potentially of cells or more, is that you can't, at least this is what the EV companies say. The EV companies say that you can't measure on each cell because it complicates, it's too expensive basically. And so oftentimes you measure a series of cells together, and your battery management system is trying to protect the cells, deliver what you need out of these packs of cells in terms of balancing individual cells. So no two cells are exactly the same. So, do I overcharge one when I'm trying to charge all of them? Do I under discharge one when I'm trying to, when I'm going through this discharge process? So this whole measurement system is extremely important to the safety and health of batteries. And in fact, there's a whole term of state of health associated with battery systems. Okay, despite all these sort of potential protections, obviously failures occur. And so, there's sort of like, the way safety is considered then is that, well, there may be manufacturing or defects in preparing cells. And this is generally considered a relatively low number, 1 in millions. I don't know what the exact number is. I don't think anybody does. But, it could be, it's a system. So it could be the charging system. If I overcharge batteries or undercharge them or charge them too fast, I could create what's called electrical abuse. Obviously, an accident or some sort of penetration is going to cause what's called mechanical abuse. And, frankly, fires happen. Fires happen before lithium-ion batteries. Fires will always happen. They follow us on ships, on water, in space. So thermal abuse happens. In all these cases, you're going to get some sort of short-circuiting inside and heating and then internal reactions and then this propagation process. Now, in some fire dynamics class, somebody talked about a Semenov analysis. And so Semenov analysis is super powerful to fire engineers and fire scientists because it says, hey, whenever I have a nonlinear chemical reaction that might occur inside a cell, inside a ship in a grain or storage, inside something that is just heating up because of degradation reactions, I get some sort of exothermic reaction. So the typical example we always talk about is linseed oil, rags, and sort of like spontaneous combustion, right? So it's this idea that I get a runaway thermal reaction, I just can't cool it. So if I can cool it, this is the cooling line, this is like Newton's law of cooling. If I'm cooling at a rate that's faster than the rate of generation, I lock in basically at a point. I can either drive it down here or potentially if it's over here, then it might migrate over there, but at least I'm stable. But the problem is that if I have a cooling system that's less than whatever my heating rate is, then I can run away in terms of the energy. So that's going to be an important diagram that we're going to come to. I'm going to just talk a little bit about manufacturing defects. So one of the obvious manufacturing defects that people talk about is electrical abuse associated with lithium, palladium, and dendrites. I think the simple way of thinking about this is if lithium ions are shuttling from the cathode to the anode and they have to fill in these porous particles, these graphite particles, if I'm driving to, okay, so let's think about the graphite particles as a parking garage in New York. And and there's a concert going on, and there are a lot of cars that are trying to fill this up. And even though there may be spots in there, there's going to be this huge traffic jam outside that parking lot. And so we see all of a sudden the growth of particles or cars outside the parking lot, and then they start to sort of migrate further and further away. Other streets become blocked, and eventually they penetrate the separator, which is the electrical insulator between the cathode and anode, and create a short circuit. So this is really just about the rate at which these lithium ions can either get into the structure of the anode or pile up outside of the anode. And so these are sort of diagrams from this paper on the detection of these dendrite particles. Another way, so practically this is the way we did it. We took these little cells and we just charged them like crazy. We just ran them hard, and eventually they caught on fire. Big surprise. But the issue really was, we said, okay, listen, is there a simple model that can help us understand how this happens, and can we use that then for other things? And one way to analyze batteries is through equivalent circuits. And so those equivalent circuits could have, two transient sort of elements for two different time constants. open circuit voltage, which is sort of like the native sort of capacity or ability or voltage associated with that battery. And that thing depends on so-called the state of charge. Is it completely charged up? Is most of those lithium ions on the anode side, or is it discharged and most of them are on the cathode side? And so depending on, you solve, I mean, this is a really simple set of equations to solve, and so you solve that, and it really sort of mimics this as long as this has been calibrated, and you get sort of good agreement in terms of the temperature that's going on between the experiment and the model. A couple things that we threw in there, though, is we threw in, from some of our other work, the rate at which the side reactions or exothermic reactions might happen, and I'm going to say something that's just kind of, okay, so in the Semenov analysis, I'm just going to, in the Semenov analysis, the whole point is that, you normally you balance the nonlinear energy generation with heat loss. But what if there's sort of additional heating because of the battery? And this is, this is like Joule heating, and then this is a reversible heat generation that happens in batteries. Well, what if there's also this additional? Well, there are two things. It makes it look like there's not as much heat loss, or that there's more generation. So that additional heating from the battery makes it more unstable. All right, so a lot of what we're talking about ultimately is going to be about the safety of these systems, and so let's just make sure we understand where the safety is. The safety happens because we get reactions either on the anode or the cathode. For many different lithium-ion systems, we get actually some sort of oxygen release at the cathode. So even inside this cell, we get hydrocarbon gases either from the carbonate, from this electrolyte, or we get from the decomposition of this. There's a binder in here, there's a plastic binder in here. So we get hydrocarbons formed, and then all of a sudden you get thermal decomposition of the cathode. You only get thermal decomposition of the cathode when it's unstable, when you've pulled lithium ions out of it. If it's stable, if it's not charged, it's actually very stable. Lithium iron phosphate, which had a relatively low energy density, it doesn't decompose and pull off oxygen, so it's considered a safer chemistry in that way. But when all this stuff happens, some of the gases you can produce are hydrogen, carbon monoxide. We just lumped all the hydrocarbons here, total hydrocarbons, and CO2. And so, we're doing a literature survey of just understanding, hey, all these cells seem to produce hydrogen. All these cells, produce varying amounts of CO. It depends on the state of charge. It depends on the chemistry. So trying to understand that a little bit better. So the way that we've worked on these types of systems in my lab is we're increasingly looking at even sort of small scales, like particles, milligrams of particles. This is almost like the flammability stuff in fire, to just understand how things go. But then we also, have this room scale environment where we can fail batteries. We fail batteries in pressure vessels so we can collect the gases. This is called accelerating rate calorimeter, where you can understand the heating processes that are happening with batteries. And there are a lot of measurements you can take. You make measurements of the composition, the elemental composition. So this is a user facility at UT Austin. I'm sure UT Dallas has the same thing. And so we do energy dispersive X-ray spectroscopy or X-ray diffraction and try to understand the composition of the materials. And I'll show you something about that, because from a forensics perspective, wouldn't it be great if you could figure out, this is something that continues to hit us and continues to hit me sort of in terms of forensics is, hey, did this particular battery cause the fire, or was it attacked by the fire? And so that's an important question and issue, and we hopefully try to understand a little bit about that. So one of the things that we figured out is, again, on top of the compositional issues, we figured out the flammable limits, because if you know what the composition is, you know what the flammable limits are. Why is the flammable limit important? Well, the flammable limit is important because then it tells you potentially if an explosion might occur, or if it doesn't occur, are you below the flammable, so below the lower flammable limit, are you above the upper flammable limit? What are the issues associated with it? We can calculate, and we're looking to soon start measuring that ourselves, the laminar flame speed. So again, from an explosion perspective, that's important. And we can figure out what the gas volume is as a function of the capacity of the cell. So this is liters per watt hour. So I'm going to use later on this idea about, sort of rough rule of thumb, 0.5 liters per watt hour. And I think that's going to be, it's important. And so I use that every time I think about battery systems. So this is sort of relatively newer stuff that we've been doing. So this is a battery you fail inside this box with a nitrogen purge. Nitrogen purge so it doesn't burn. But everybody here knows that hydrogen fluoride is very dangerous. And the immediately dangerous to life and health, this IDLH value is about 30 ppm. When these cells fail, and so this one is a lithium nickel manganese cobalt oxide NMC cell, and this is a lithium iron phosphate cell. The amount of HF produced in this system is over 1,000 ppm. So we're producing over 1,000 ppm, we're not. The battery's producing over 1,000 ppm of HF as it's off-gassing. So, being right over it, you see the YouTube videos of people sort of like over, I don't think anymore potentially, but over batteries failing, obviously not a very good idea. And so it doesn't matter what kind of chemistry it is. These are sort of like, those are the values and the abundance of HF that's being produced in these types of systems. So very dangerous. And then sort of another sort of useful rule then is that we find, and we have looked in the literature to confirm, that there's about 30 milligrams per watt hour of HF that's produced. And again, I was talking to Justin about this, about what the implication is, and we don't know what the implication is because HF is so reactive and so sticky that it's not obvious if it gets out. Like, it may be produced inside this compartment that holds batteries, but by the time it gets out, maybe it's already reacted with the walls or with other things. I think that, the gases that are produced, even though they have that hydrogen, they also have CO2. So the CO2 sort of like is a diluent. It brings down sort of the reactivity of the system. So it looks a lot like propane in a lot of cases. So, in terms of, again, trying to think about, am I thinking about some exotic mixture? No. It has a heat of combustion that's about half propane, but it has, say, similar laminar flame speed. So, all right, so, when the media talks about battery failures, New York City has seen an epidemic in e-mobility device fires, e-bike fires, and all these other things. And I think we are all concerned about this. The thing that's interesting, I think the thing that's interesting is that, all right, so the first thing is if a DeWalt drill pack, I'm not, picking on DeWalt in any way, but, say 20 volts, 3 amp hour. So using what we already talked about, if it's using these 18650 cells, which are about 4 volts and about 3 amp hours, so to get, I use 4 volts here. So using 4 volts, 5 times 4 is 20, so I need 5 of those in series. Because these are 3 amp hour, I just need 1 in parallel. So I just need 1 parallel strip of these to get my 20 volts, 3 amp hours. Now, my overall capacity then is 4 volts, 3 amp hours, times 5 of these cells. And so 2060, so I got 60 watt hours. So if I use my rule of 0.5 liters per watt hour, I get 30 liters of gas. Okay, so it's a relatively easy calculation to do to understand how much gas is produced for this. Now, I'm gonna tell you again, the energy sort of like of combustion is about 20 kilojoules per gram. So it releases 600 kilojoules, which sounds like a lot, but we'll be careful and think about this a second. And so we could do sort of like the same exercise for an e-bike or a residential ESS that is a 5 kilowatt hour system. So we can calculate, we can first of all use our rules of, depending on the type of cell that I'm using, I can figure out how many cells of those type and the voltage of the cell. I can figure out how many of those are required to get to the voltage of whatever the appliance is. And then I can think about how many parallel strings I need to get to the overall capacity. So, what's a typical fire department response time?
And 1710.
Yeah.
It's around, there's different thresholds, but somewhere between 5 and 10 minutes.
I feel like 5 minutes is a good number. So I'm like, okay, if I look at 5 minutes and say this thing has been failing over 5 minutes, because there's a propagation process that occurs, it's cell-to-cell propagation. Interestingly, each of these cells might fail over 5 to 10 seconds, but the overall propagation might take minutes because there's sort of intermediate times and all sorts of other things. But when you look at that, you're like, average heat release rates of 2 kilowatt. Who cares about a 2 kilowatt heat release rate? I don't care about that. You know, trash can fire is like, help me, Justin.
1 megawatt?
Oh, I think like 100 kilowatts. Yeah, for trash can fire, that's what I think. Yeah. Okay, I mean, you have bigger trash cans than I do. But we're talking about nothing, right? These are like nothing heat release rates. But the reason is because it's directional and it's really concentrated in jetting, and we'll see those in a second. So I'm going to talk about suppression and ignition then. Okay, so if you stick a battery inside a foam cap and make sure that the sparks don't come out, you just get a bunch of gas. If you stick it with a more porous foam cap, you get the sparks that do that ignition process. When we measure the temperature of those sparks, they are hot. And so they are, thousands of degrees, 2,000 Kelvin, and so we want to understand why these things are as hot as they are. It's sort of inconsistent, potentially, with combustion reactions that are happening inside. And so we want to understand that. We look at the velocities, and so they're jetting out at 10 meters per second, 20 meters per second, et cetera. So why this is useful, I think, for a couple of reasons. It's useful potentially in terms of our understanding where to find sort of incendiary particles that are emitted from batteries as they fail. It's important in terms of thinking about sort of where the ignition sites might be. So again, we can suppress ignition like in a nitrogen environment, and if we don't suppress ignition, we get these large flames. When we measure the heat fluxes off of this and the flame length, we're getting 430 kilowatts per meter squared. So, again, sort of conventionally, we think about sort of like a critical heat flux. I think about somewhere between 10 and 20 kilowatts per meter squared. So, these are, more than direct flame impingement. This looks like, sort of like a premixed flame like on a wall. So this is the safety hazard. It's the jetting. It's the fact that this heat release is occurring over a very short duration in a very directional manner. From the forensic side, a couple of things that are interesting, I think, and that are takeaways. FAA and other transportation groups recognize that the state of charge, this was not recognized initially. Unfortunately, societally, we've lost cargo planes, maybe even passenger planes because of battery failures. I gotta check my watch. And so in terms of that, there's a recognition now that if you have cells below 50% state of charge, it's, so what we did here is we put a battery and thermally abused it and put it over polyurethane bedding material. And one of the things is that below about 50% state of charge, it doesn't ignite that material. Above, well, it's a different issue. So state of charge is probably one of the most important parameters in understanding the ability of a battery to cause secondary ignition. So the other interesting part is, at least for these cylindrical cells and NMC cells, is that if you look at the amount of mass that's lost as a function of the state of charge, you lose, so this is a 45 gram initial, you lose about almost half of the mass if it's a fully charged cell. You're barely losing anything if it's not. So from a reconstruction perspective, if you have that cell and you weigh it after the fact, you are more likely to understand what the state of charge is. If you understand what the state of charge is and it's low, you're more likely to recognize whether or not it was the cause of the fire or if it was attacked by the fire. So that's one thing that sort of like we think is an important finding. An interesting finding that we still have to, we've published the preliminary results, is that there's a difference. So once you find these batteries after failure and you measure the elemental composition, say in this nickel, manganese, cobalt cathode material, you measure the nickel to manganese composition or the cobalt to manganese composition, something really crazy happens. You find out that there's sort of a stratification in terms of the nickel to manganese ratio after failure compared to the pristine. So as you go to lower states of charge, it looks more like the pristine, but as you go to higher states of charge, these more energetic and dangerous cells, it changes. And so is this a marker? Well, that's another way that we're sort of thinking about this, and we're pursuing research on that. So, okay, so a battery is a pilot. You know, to first order, all sort of solid ignition problems look the same. You have source energy exposed material, you produce flammable vapors, you have this pilot source, the incendiary particles, or the cell itself, flame, and keeps burning. I'm going to try to say now that the most important, sort of like the biggest hole in understanding battery failures at site scale is the propagation that happens from cell to cell. It's not the failure of any individual cell. Any individual cell is just a single fuel packet. It's the propagation to adjacent fuel packets. And so that rate of propagation is a rate of gas generation, which is a rate of heat release, which is possible. Then it's something that is harder to defeat in terms of ventilation or air exchange if you're trying to reduce explosion hazards. So this is a IE-tron sort of battery pack, and we've seen a lot of battery packs like this. Hyundai has battery packs that look exactly like this, where it's just, you know, stacked pouch cells next to each other. So we said, okay, let's duplicate that in the lab by having a bunch of stacked pouch cells, and let's use a single heating on one of those to initiate it. You say, well, that's cheating. No, we're saying that any cell can potentially fail. What's the consequence of that failure? So if a cell fails, what's the consequence at larger scales? And so, you know, afterwards it burns up. Big surprise. Okay, so one of the things that's useful there is we have some rules about what the rate of release or the rate of propagation is for these different types of cells, because we can say, you know, for this, you know, particular cell, the liters of gas generated per second per watt hour is something that we can find. And then we sort of think, because this is done in a pressure vessel, and so we measure the vessel pressure, and we can figure out, again, the amount of gas that's generated, and we can actually model that. So again, these are sort of like nice takeaways. But then later on, Robert Kennedy, who's my PhD student working on this, he's working in commercial space now, working on battery systems for space systems. Started doing sort of like, you know, modeling on that to figure out, can we predict, these are thermocouples between each layer of cell, can we predict when each layer of cell then sort of goes up to these high temperatures, about 800 C. So after failure, it's 800. So this looks a lot like a premix flame, but are there things that happen that we can then change that? And one way to change it is separation material. For example, an insulating material or fins or otherwise. So what's the takeaway here? If I have no separation material, it might take 80 seconds to propagate. With separation materials, I can extend that to 400 seconds, say. So that's a huge decrease in the heat release rate. It's a huge decrease in the rate of gas generation. It's a much more manageable threat. We did things like, you know, failing laptops to see what the heat flux signature is a meter away. And, you know, again, not surprisingly, very high heat fluxes, 7 kilowatt per meter squared, away, removed from the laptop failure itself. And then we see the propagation within the cell between the adjacent cells. And Corey Yan, who's now, he's working at an EV company. So we said, hey, listen, is there a way that we can, rather than externally heating a cell, can we put some sort of heating element inside a cell so it's non-intrusive, so we can fail a cell from the inside? And so that's sort of something that I think is pretty cool and that we can then use for understanding other failures. Okay, so the last parts I'm going to talk about are really consequences. So far we talked about single cells and little arrays of cells. But, you know, if you've got thermal runaway, you can either have no ignition or immediate ignition. If you've got immediate ignition, you've got a fire. This group knows how to deal with fires. You know, there are a lot of ways to suppress fires. But if you do suppress the fire, what happens then? Well, then the batteries keep potentially off-gassing. So suppressing the external gas phase combustion process doesn't mean that the cells aren't propagating. We did these tests in an inert environment. There was no fire, it was in nitrogen. The cells propagated to each other. So you are still going to produce a flammable gas environment that could explode. And we've seen explosions all around the world associated with this, and we're starting to see it in residential systems. There's a question of what the downwind plume looks like, what the composition is, and so we'd like to understand these issues better. So we started, we did some testing at room scale, and first thing we do, of course, was we figure out how single cell fails in terms of the release rate of the gases and also the composition of the gases. We instrumented up our burn structure with this 5.5 kilowatt hour module, and let's see, I should be able to. Okay, so this is the first cell failing. These are 6-7 foot long flames, and this is just the first cell failing, and it just cascades to all 14. And with the sound, it sounds like a freight train. It's the roar of it is incredible. So again, and that propagation process occurs as it moves through. So when we look at the time over which this occurs, it happens over about 1,000 seconds. So over 1,000 seconds, it's like cascading to next and next and next. So when I put earlier on, what's the average heat release rate there? It was nothing. It was manageable. But when you look at it in this way, where it's directed and very intense, it's kind of scary. And so, so we look at, say, the mass loss. This was on a load cell, and you see that after the first cell fails, it takes a while for the second cell to fail, takes a while for the third cell to fail, and then just like falls off. Said differently, the number of cells failing, it's like over the first few hundred seconds, first few minutes, it's very slow. But then after that, it becomes very difficult and very uncontrollable. So, from a consequence modeling, if I want to understand maybe what the fire protection systems are, what kind of barriers I need, you'd love to be able to model it. So what we said is like, okay, well, let's model this with FDS, and let's look at the equivalent battery gas sort of composition in FDS. Let's look at the heat fluxes and temperatures that we measure in FDS compared to what we did at the compartment. It's okay. It's not good. It's okay. It's better than me guessing before we did the test what it would look like. But there's a lot of room for improvement in the models to be able to and in the modelers in terms of our ability to figure out what these systems should really look like when they fail. Surprisingly, it does a reasonable job in terms of the measured gas composition. We're just looking at CO2 and oxygen. So, the trends are right, if nothing else. Something I'm really excited about is, you can't always run FDS. So is there something better? So, like we said, okay, well, listen, if we just write some equations for each cell, how well does that do? It's not horrible. And I'll tell you what was really surprising that we learned from this, and we're still going on with it, is that it's mostly radiation. So I would have thought that it's convection, that, like the reason for this spread was all these other factors, these cells are spaced. It's actually a radiation problem, so that's kind of cool. Here we were doing a test where we had one of those single cells inside a closet, and it causes an explosion. Not surprising again, because we vent these flammable gases as a delayed ignition process, and so we'd like to be able to predict that. So, it's stratified. So when this venting process occurs, at the top, it's about 1,000 Celsius. At the bottom, it's much lower temperatures, even in this tiny little closet. And so we have not been very good. We've not been able to do a very good job in terms of modeling it, but it's not a big overpressure, 0.01 atmosphere. And so we're just trying to understand first, it's something called a partial volume deflagration. It's not a well-mixed, the old days you say it's a stratified mixture or something like that. It's not a well-mixed system. I sort of believe that simple models probably make more sense than really complicated models, but that's an issue. And I'm going to point, the only reason I'm pointing this out is not that you're going to solve these equations, but in these equations, For the burning rate, the parameter that's most sensitive and the most important, we have nobody here, nobody outside has any way of really figuring that. It's a turbulent burning speed. So turbulence, the stories are that Einstein gave up on fluid mechanics because of turbulence and went into something easier like quantum mechanics. So turbulence is hard, it still is, right? And so we have no idea what to do with that, and I'd argue nobody does. So like there are people who spend their whole careers trying to figure out turbulence. Not me, okay? But I will tell you this. So what's interesting to me about this is that, battery explosions are not the first place people are concerned about explosive systems. And so in hydrogen safety, and especially in Europe, people have been concerned about this for a long time. And so there's a whole sort of software package system called Open Foam, and then there's a High Foam, which is hydrogen safety. Some of the people here actually use FLAX, the GEXCON code. And so when you look at sort of like, against experimental data, here's test data. Here are different grid sizes. It's not like it gets better as you go to smaller grid sizes. So one of our discussion points, like our Lonnie was talking earlier about the effect of grids, right? I mean, grids are important, but it's completely counterintuitive that as I go to a finer grid, I get a worse result. Okay? And then, it was as a blind prediction and competition. None of these code sort of bases are going to do a great job in exploiting. It is really hard, okay? It is super hard. So I don't know what we're going to do about that. And I'm going to wrap up. Here's something scary to me. So this is hybrid Jeeps. These have just been recalled. You see the firefighters, this is in Ghent in Belgium. You see the firefighters here, you see sort of the civilian here, not on air, just wafting in, taking it all in, And then here in Florida, this response, this is a Tesla, sorry for people who own Teslas, it's failing. And the firefighter's not in air, not trying to throw the firefighter under the bus. And this person, so there's a lot that we just don't know or we haven't communicated about the hazards. I showed you 1,000 ppm HF. Okay, it may be not 1,000 here, but it's not minuscule, right? And so there's some hazard associated with that. And then on top of it, the fog is a fuel. And so this is, the HF story is a big issue. The dimethyl carbonate, the solvent, is a big issue. How much time do I have? Like 5, 10 minutes? 12 minutes, okay. So now I'm really going to ramp it up, okay? So those are all issues that we have to think about. So Justin asked, he's saying, listen, what about emergency response? How far away should we position fire personnel who are not on air, potentially, incident commander or others, away from this? So we looked at the literature for, say, HF, CO, SO2 associated with lithium-ion battery failure. And so remember that 30 milligram per watt hour number. So this is times 10 to the 2. So it's 0.4-ish times 100. So about 40 there, but about 30 at this high stated charge. And we looked at, for all the different sort of data sets out there, we made a determination about the value relative to the IDLH value. So we normalized by IDLH. And, most things were below IDLH. CO, sort of like below IDLH, SO2 below. HCl, there's certain cases they see HCl. All right, but HF is the scary one. And so we said, okay, maybe we should be doing plume studies to understand what the downwind distance over which this persists is and when it's still above IDLH. And so that's what this study was looking at. I'm going to just summarize it. So we did sort of an uncertainty analysis and all this other stuff. Just using the raw data, there are 2 cases here. Case where the battery gases are burning is red. Cases where the battery gases are not burning are blue. So battery gases not burning, in this case, give a safety distance of about 40 meters compared to burning. Why is that? Well, when they're burning, there's this huge plume and it takes it up and it doesn't take it downwind necessarily. So having stuff that's burning and it's being lofted into the atmosphere is probably safer than if it's cooler and it's just blowing right downwind. So, and then, there are slight differences that are associated with that. Because of the uncertainties in some of the parameters, we sort of say that about 100 meters, and that, this is from the modeling, is about a reasonable estimate. EVs versus internal combustion engine vehicles, is there a difference? Not according to these calculations and not according to what the Swedish rescue services did, RISE. So if you look at the heat release rate from EVs compared to ICE EVs, they're about the same. And if you look at the toxicity, there's not a whole lot different. They're all bad, don't breathe it in. So I don't know what to tell you there. Fire, all smoke is bad, but maybe some smoke is worse, and that's what we're trying to really understand. Fire suppression. So if I've got these batteries and they're sort of popping off from cell to cell, and then I have some cooling agent that I'm dispersing on it. Well, there's nothing I'm going to do about that first one that's already in thermal runaway, but maybe I can affect the other ones. And so that's an important issue. So suppression systems could extinguish the flames, but that doesn't do anything because it may not extinguish the propagation. And say I cool this guy, and I shift from, say, natural or whatever convection to a much more intense cooling, and all of a sudden I stop that. It's unlikely that I'm going to keep that on there forever. So when I remove it, it may start to migrate. So we've seen, you all know about electric vehicles and otherwise, that firefighters or others control the incident, but a day later, a week later, there's continued failure. Now, there could be a lot of reasons. There could be corrosion, internal shorts, external hard shorts. There are all sorts of reasons that could happen, but it could just also be that the reactions finally just take off. They could be slow reactions that are then taking off. The bigger issue with suppression is that, as we've seen, is that in a lot of cases, it's Fabergé eggs. You've got batteries and containers and containers and containers, and so when you have layers of containers, how are you going to get your agent on it? At best, you cool the container, but there's nothing obvious about your ability to cool the cells. That's a challenge. So one of the ways that some firefighting groups are thinking about this is with these sort of insertion and penetration and piercing nozzles. And, again, I don't know. We've never done the research on that, but that's the idea. That's the reason to do that, is to get the water where the cells are. I think this is a great paper, and I don't have time to talk about this. It's a paper out of China, a review of fire extinguishing agents and fire suppression strategies. So we haven't done all these tests, but it's sort of like a comparison of all different types of cooling extinguishing strategies in these so-called spider diagrams, where it looks at the cost, the residue, the toxicity, is it insulative, cooling capacity, and what's the overall extinguishing capacity. So, I'd love to sort of at least understand where their data are coming from and how good, just even as a sample for some of these cases. Okay, in 2 minutes, explosions happen. What are ways around explosions? NFPA 68 is one way. So actually NFPA 68, there's a lot of push for, NFPA 68 is a standard that says that we are going to have deflagration panels. That when we have let me go back. So this is a hydrogen experiment. This container's full of hydrogen, it's ignited, and the container's not rated for the overpressure that would occur if this thing just was ignited inside. And it's highly uncertain what directions fragments would go. So the idea of a deflagration panel is, let's create known failure points on that container so that we direct the failure in a particular way, in this case, up. And so that deflagration panel, and then there's a design for how many of those deflagration panels you need. What's the area of those deflagration panels, all dependent on your composition, the overall volume, the amount of tortuosity within there, because that accelerates the flame to the extent that we don't know really how much. But so that's what a deflagration panel is, and that's explosion protection. It doesn't say that it's not going to explode, it just means that we know which direction it's going to explode. So to do that type of calculation, it's really a mixing. So this is a BESS with one of a battery energy storage system container where it's mixed. The way that this is done is there's an NFPA 68 standard, which is the lowest order model that you can put in for that. But, the big hole again is the turbulence. There's a question of is this conservative? I've seen papers that say that this is not conservative, and studies that say that this is not necessarily conservative. So I guess, again, there's a lot of unknowns there. NFPA 69 is another way that we sort of try to deal with explosion hazards. NFPA 69 says that we don't want the mixture inside to globally go above 25% of the lower flammable or explosive limit. And so the way that that's conventionally done is with fans and louvers to mix in air as the battery gases are coming out to make sure that that doesn't happen. How would you size that though? So the only way that you could size that properly is what the gas release rate is. How do you know the gas release rate? You need to figure out what that cell-to-cell propagation is. So cell-to-cell propagation is the big hole in so turbulence is a big hole, but cell-to-cell propagation is another challenge in our understanding of even sort of engineered fire and explosion systems. And so, here's a ventilation system that maintains it, and that works. Pacific Northwest National Lab has something called IntelliVent, and one way they say is that they're going to, as soon as they smell battery gases, so that detect battery gases in the containerized system, it's just going to open up the doors. Okay, that's pretty smart, but what if there's an external fire that causes the smoke to penetrate in and it opens up the doors that way? Could that cause an unintended consequence? Maybe. And so there have been sort of reliable detectors have been the source of failures in other systems, and so we don't want that to necessarily happen. Alltech, I'm involved in Alltech. It's a startup company thinking about other systems for maintaining it. It's a scrubber, basically. It pulls in the battery gases and converts them into CO2, H2O, and redirects them back in as a clean agent. So there are lots of solutions that are being put out there. All right, so I guess what's my sort of story? I think that you have to look over a range of scales to be able to do these types of problems. I think the cascading failure is what we're really trying to understand. I talked a little bit about the flammable gas composition and volume. Those are easy to characterize. Rated gas generation for cell-to-cell propagation and for toxic gas composition is harder. And proper design of deflagration vents is limited by turbulent burning rates modeling, and that's a big issue. And when we're thinking about it in general, there's a lot of engineering that has to take place for these types of systems. So what am I trying to do? I want to understand what happens at the site level. But it's become increasingly obvious to me that I need to understand more what happens at the materials level because material scientists, and hopefully there are no battery people in here, but there's a long history of exaggeration in the battery sort of like materials community about what batteries can and cannot do. Early on, we always heard, my battery is never going to catch on fire. Well, then it did. So we want to be on top of what modifications are happening in battery chemistries, even if it's just for the toxicity. So even if it's not because the batteries go into thermal runaway all the time, we want to understand when the fire occurs, because it will, we know that, what's going to be the toxicity and what are the issues. And we should be able to run all the way to what that site consequence is in terms of the emergency response, in terms of the plume, et cetera. All right, thank you for your attention. I really appreciate your time. Again, thank you for the invitation to be here.
So we'll take a sec for questions. So if there's any questions out in the audience.
Thank you, Doctor. So my question is about the state of charge. So in the lab setting, it's easy to, I would say easy. I assume that it's not incredibly challenging to figure out what the state of charge is on a particular battery. In the field, how can the authority having jurisdiction or the inspector or whoever that is, how can we assess what a 30% state of charge is
Okay, for a non-failed battery, right?
for a non-failed battery? Think of it as in the fire fatalities in New York, for example. They take that battery out of one device, it sets on, they're getting it prepped and repurposed for another device, and that's where it failed. For example, in the upcoming fire codes, in the 27 fire code, or I'm sorry, the 24 fire code, it is focusing a lot of energy on when a battery that's used for a micromobility device, if it's less than a 30% state of charge, oh, you're fine, you can have up to so much amounts. Once you go over 30% state of charge, well, now we need to start doing stuff. So how can we assess what that state of charge is?
Okay, thank you. So I would argue that actually it's hard for everybody to figure out state of charge because if vehicle manufacturers even understood the states of charge for their cells, then the range would be a much sort of clearer range prediction. So funny enough, it's like there are questions about what the state of charge is even for something that is going through a particular drive cycle. So state of charge can be hard. So sort of the way that, you know, from a lab way to do it is you Coulomb count. You discharge to what the sort of cutoff voltage is, and then you integrate the current to what the sort of like the top voltage is supposed to be for that cell, and you know how much capacity it is, and then you can sort of back off and understand. And so it is hard, and that's not, you know, like, I listen to and I talk to battery folks in our, who we're collaborating with. They're sort of like two states of charge. There's a state of charge that is the electrochemistry, that is just what the material can hold, because I was providing that diagram. It's like, oh, the cathode can hold 150 milliamp hour per gram. Well, no reasonable battery manufacturer is going to use that theoretical capacity as what their 100% state of charge is. It's always derated all because of safety and other considerations already. So in some sense, we have to trust the battery manufacturer to give us sort of the specs of what the limits are for that particular cell and cell chemistry. And then either, you know, you have a battery cycler then that you can, you know, charge up to whatever they have told us is the right cutoff voltage and figure out, oh, it must have been at this value because it took this amount of current to get it to 100%. So it's not easy as far as I can tell, okay? So I'm going to go with that. And then here's the other side of it that's even worse, is that there's a parameter I didn't really talk about, which is the state of health. I don't think I mentioned state of health, but the gas can is shrinking. So the capacity is shrinking over time. The ability of that cell to take in charge is reducing with degradation and with time. So, you know, this idea of, you know, is 30% state of charge always 30% state of charge? I mean, there may be a cell that 30% state of charge is all of a sudden 100% state of charge because it's so degraded, you know? So I'm sorry, I certainly don't have an easy answer for that. And if I did, maybe, you know, there'd be some tool or paper or something that we could sort of like put out there, but I don't know what the easy answer is, but I'll certainly talk to my sort of battery colleagues to figure out if there are simple ways of assessing that. Thank you.
Any other questions?
At the risk of asking a stupid question,
Oh, no.
I was kind of way at the top end of my understanding, but in the fire service, the concern with, as he said, micro-mobility devices is people come in, they drop their scooter next to the door, and then they wake up, the fire started, and it's trapped inside, and it ends up being a fatality fire. With a lot of the data that you presented, where when these batteries fail, they often create an environment that would be fatal within a couple of breaths. best guess from a tactical standpoint, when we have these victims that are adjacent to these areas, it sounds like there's a really good possibility that they could be very, very dead before the fire really even gets going if the battery failed. Is that a scenario that, with your expertise, you think is probably pretty common, or is it just a toss-up?
You know, I don't know if anybody's done, I haven't seen toxicological data on people who are deceased because of battery fire, like consequences. I guess.
Well, with an autopsy, you wouldn't be able to, because oftentimes the body's incinerated. I mean,
But they oftentimes can tell by inhalation. They can sort of figure out about carbon monoxide and potentially other hazards. So what's interesting is that I've seen, sort of like CO being elevated, but I don't know if it's HF has been checked or if any associate. You see sometimes they'll say chemical burns. And so it might be the HF. I mean, again, I don't think we have a good sense. I mean, we sort of as a community have a good sense about what might be happening when that e-mobility device is at, like you said, at the doorway or right outside inside of the hallway or whatever. I don't think we have a good sense of whether or not it's part of the. I personally would feel that it's not. Okay, I really strongly feel that it's not. I feel like it's really the ignition of everything else around it that's causing the fire to be challenging for people to get through. But then on the other hand, like I'm measuring these ridiculous sort of concentrations, and I don't know where that stuff is going. So, I hate to say more research is needed. I sort of feel like I can't answer because because I've seen the data, so yeah. Great question. It's not a stupid question. I have no idea.
well, thank you for your
Absolutely.
Great question. The spider graphs that you were showing from the China research study, any recommendations for EV owners?
I don't want to.
Come on, we need an endorsement.
Look at you. You're trying to pull me into a fray here. I think there's a question.
You mentioned the thermal runaway and exposure protection systems for the big room of batteries. Have you seen anything like that for smaller energy storage systems, like for an EV or a residential area?
Okay, I'll tell you. Okay, I'm going to answer this a couple of different ways. You know those like little bags that that are sold on Amazon to contain battery failure?
LiPo bags.
Yeah, LiPo bags, exactly. So we're just messing around, but we did a demonstration. We bought 5 or 6 of them, and we stuck an 18650 in each of them, and most of them just burned up. And we repeated it, and the ones that didn't burnt up the second time, and so those don't work. Yes, I'll tell you that right now. Okay, so, but in terms of sort of at garage scales, I think that we're close on this all-tech solution in terms of, it's an extractive method. So, I think it's the same idea. It's a ventilation-ish type strategy would work. But I don't think anybody's really engineered it at that scale for a commercially available product. There's a question.
Yeah, so my question is going to be, what in your opinion, because we're over really early on here, is going to be the move for the early detection where we're dealing with these batteries, especially we're putting them in cars, we're putting their places. Are we going to go with gas detection? What is the earliest detection we think we can find? Should we be looking at to catch this fire as early as possible? Because it seems like obviously we get a lot of gas release. We're going to end up in a lot of trouble before we even have the ignition source. We can't do our normal heat detectors. We can't do our normal flame detection, stuff like that. Is it all gas detection? What do you think the move is? I'm pushing the spot, but that's
Okay.
we'd like to know.
Yeah. If it's gas detection, it's probably the carbonate. And some VOC detectors can do that. What's weird is that it's the designs may not be all sort of like, for good reasons, moving in the same direction. If you've got a prismatic or a cylindrical cell and it builds up to high pressure, it's going to release all the gases about the same time. So you almost have no opportunity for early release and early detection. What you really want is you want something to be released at low pressure before the violent thermal runaway happens. So the carbonates, as soon as the cell starts to get hot, the vapor pressure of the carbonates increases enough that they want to leak out anyway. So if in a pouch cell, you get a pouch cell starting to leak out really early, you know, because it's really compliant, and so you have this liquid in there, it's starting to get hot, and it just wafts out, and you see the vapor, you smell it, and so that stuff is really early. That'd be a great early detection. If it's in a container that has a high pressure vent, that stuff isn't coming out. It's cooking inside with all the other really bad gases, all the really bad flammable gases, and then they come out all together. So one thing is it depends on the packaging. The other thing is that, I didn't talk about it here, but I was working with one of our colleagues. We did a series of research projects and students working on ultrasonic detection of battery failure. And so ultrasonics can detect, it's basically non-destructive testing. And so they can determine and detect even before there's a failure, just that there's this cell is going bad. And so we've only done it for pouch cells, but I think that's a really early one. I think that the OEMs in the EV marketplace are not going to do things like that. I don't think so, because it's probably too expensive, at least right now, and too much computation potentially. We think that there are ways around that, but but yeah, early detection is the question, but it's a system issue basically.
So, follow-up question to his on the detection. So, if you have a Tesla Powerwall or other competitor brand battery wall, we'll say it's 19.9 kilowatt hours. So, on that, are you saying that it's better to have thermal detection either as a sensor pointed at the chassis system or the wall, or thermal detection within each battery, I'll call it system, battery packs, because they typically have 4 to 6 battery packs within the wall? Is it better to have thermal detection within the cabinet, within the cavity? And is that going to be better than the gas detection because of the time for ejection?
I mean, ideally it'd be great to have both. Again, I have a residential battery energy storage system. It's on the outside of my house, not in the garage, and because this is a Austin sort of issue, that Austin will not basically allow you to have it inside your garage unless you have bollards, and so also in your garage is not useful. And so this is a weird story, and so you get more degradation because it's hot all the time, but it's safer. Okay, but I think about this honestly, and I think, okay, well, what kind of detection? What do I want to do there? And I feel like if gas is more reliable, I think it would be a gas sensor, and because of the fact that it's probably 18650s. I mean, for my particular system, it's probably 18650s. We've tested both sort of cylindrical cell battery energy storage system and prismatic. I think that it's going to vent the carbonates at the same time as the flammable mixtures. I suspect that it's not going to propagate cell to cell, because I think for those small cells it's more challenging to do propagation cell to cell. But I would have it located at the top of the cabinet, basically. So I would have, just a gas detector. It honestly could be like a, hazmat for gas VOC type sensor, honestly, in terms of figuring out what's going on there.
Other questions? Okay, we got one right here.
So I have a question regarding, so it seems that the 18650s and the prismatics seem to be a lot more detrimental in terms of their I guess, reactions because of their explosions at the end. Has there been a push, I'm not super familiar with this, but has there been a push to go more toward the other shapes? Because I know you said the manufacturing has made it better, but it seems that if one is a lot more detectable with the other design with the packs that are thinner and longer, I'm forgetting the terminology, but why don't they push for that in terms of like codes? You know, if you can obviously be more preventative to catch gases earlier with one design, it would seem that why wouldn't that be pushed more toward that?
I think that, you know, there are competitive advantages that people find or think that they have in terms of particular formats and sizes. And I don't want to be just, you know, focusing on T650. We've tested 2170s, 4680s. And so what's really interesting is just this migration to larger cylindrical formats. And so these things sort of look like grenades. I mean, they're like, you know, like that. And when you fail them for us, you know, you see some like mass ejections. And so there's a lot of room for thinking about safety in the design. So let's assume like somebody's, you know, their overall supply chain is such that they can only get this particular type of cell. Let's assume that. The question then is, how do we engineer to make that cell safe enough or as safe as this other cell, which may have its own problems? And so I think that those might be the challenges, is thinking about it more as a system than anything else.
Good questions. Another one? Great. Well, thank you, Dr. DK. Round of applause. If you didn't register, Fernanda right here, you can get with her. You can get announcements. And yeah, thank you everybody for coming. There's more pizza outside. There's plenty. So what's that? They're out of pizza. Never mind. All right. Thank you, everyone.